Morning everyone, welcome to SRCBS Maths and Physical Sciences channel. Today we'll be talking about the section in physical science, that is about the rates of chemical reactions. Mind you, this is linking to our previous section that was talking about the energies that are involved in a chemical reaction. So for you to understand this clearly, you must have just seen the previous video where I was addressing the energies that are involved whenever a chemical reaction takes place. But today we'll be talking about the factors that affect the rate of chemical reaction. But before we do that, we'll have to look at the background that you should have on the physical science concepts so that you can understand the rates of chemical reactions. To start off with, we'll have to talk about these concepts. I've written here background for the lesson today. So what you should know what are reactants. So what are reactants? So reactants, that is a substance that reacts with another substance to form a new substance that's called a product, and that results in a change in the chemical properties of that substance. What is a product? A product is a substance that is formed when a reactant reacts or reactants have reacted. An example that I've just made for you is ammonia. Ammonia, under some certain conditions, will break down to form new substance from it, which is called decomposition, which products that will form are nitrogen and hydrogen from ammonia. The other substances that I gave an example of is when hydrogen reacts with oxygen under certain conditions to form water. Therefore, these are called our reactants, and those substances that are forming are called our products. Now, before we go any further, another very important term you should understand in chemistry is concentration. What do you mean by concentration? By concentration, you mean the amount of a substance per unit volume. Here is the formula for concentration. Concentration is equal to the number of particles per unit volume, as you can see, where N is the number of particles which should be measured in moles, volume, which must be measured in cubic decimeter, and the concentration that is then measured in moles per cubic decimeter. So I wrote for you there what the SI units are. You've got to know that this physical quantity unit, cubic decimeter, at times confuses learners. We actually mean that is the volume that is equivalent to a liter. So when one talks about 1 mole per cubic decimeter, one says there's 1 mole in a liter when one talks of 1 cubic decimeter per liter. Now, again, another very important measure of the amount of a substance is that mole. What do we mean by a mole? By a mole of a substance, we mean there are 6,023 multiplied by 10 to the power 23 particles of a substance in that volume, if it's concentration. Now, what do we mean by that? So when we are saying there is 1 mole per cubic decimeter in water, we are saying there are 6,023 multiplied by 10 to the power 23 molecules of water in that volume, which is a liter. Now note again, what do I mean by that 6,023? It's quite a big number. That is why the physical sciences people, the scientists, opted to use a mole than to express that very huge number of the particles. If you may look at it, it has got 20 zeros from my right to my left, and there is 3206 onto the left. So quite huge is a number. I cannot spell the number out myself. That is why then you would have to understand that scientific notation because it is trying to squeeze out quite a big number, which is 6023000000000000000000 particles in a substance. Hence, we opted, as people that are using science and are doing science, to call that a mole, and hence a mole is used even today. Now, continuing with our lesson, we have to look at the rate of a chemical reaction as I said and introduced my lesson. So the rate of a chemical reaction to us as people who are doing physical sciences, the rate of the reaction is the amount of the reactant or reactants that are used up per unit time, or that is amount of the product or products formed per unit time. The equation that defines the rate of reaction is reaction rate is equal to the change in the amount of a substance per the time taken by that substance to change. Remember, by changing, we mean the substance will either be decreasing when it's a reactant, or the substance will be increasing when it is a product. The amount of a substance are defined in different physical quantities. For instance, we may use volume when it's gases, when we're measuring the amount of a substance. So in that case, we may use milliliters or cubic centimeters or even cubic decimeters if you talk about quite larger volumes. Now in mass, we may, in most cases, if those are solid substances, we may use grams or maybe kilograms. And then if those substances can either be solid, liquid, or gases, we can also use moles, as we explained what a mole is. Now, what are the factors that determine the rate of a chemical reaction? So the factors that determine the rate of the reaction are temperature. Temperature affects the rate of all substances, irrespective of the phases in which those substances are. So it means temperature affects whether a substance is in the form of a gas or a liquid or it's in the form of a solid. Then the other one is concentration. Concentration mainly affects liquids. That is the reason why then when we are talking liquids, in most cases, you'll see as we make some, working on examples in our physical sciences problem, that the concentration will affect liquids. And why will it affect liquids? It is because concentration, we said, it's a number of particles that are in that volume. So if the concentration is 1 mole per cubic decimeter, and the other concentration is of the same substance is 0.5 mole per cubic decimeter. It means in a 1 mole per cubic decimeter, there is 6.023 multiplied by 10 to the power 23 of those substance particles in a volume of 1 liter. But if it's 0.5 moles per cubic decimeter, it means in that 1 liter, there is now a half of the particles of a substance that were in 1 mole per cubic decimeter. And hence, particles are closer together. And there are so many in the higher concentration substance than they are in the lower concentration substance. And that makes the reaction rate to be occurring at a higher rate. Then the other one will be state of division. What do we mean by a state of division? At times that is referred to as the exposed surface area. We use that for solids. You would understand that when we have an example, a larger granule of salt, and you take that salt, you want it to dissolve in water. Remember, dissolution of a salt in water is an example of a chemical reaction. So when you put salt in water, the particles that are outside the granule of a salt will be the first particles that will just go into the reaction. So those ones that are covered by the outer particles will remain safe whilst the reaction is taking place. Only when the outer particles of a salt granule have shed off, that the inner particles will then also go into the reaction. In other words, it means the reaction rate for the inner particles will only take place provided the outer particles on a granule, on that larger piece of salt, have gone into the reaction. But when you take another piece of salt of the same size, same mass, you grind it into smaller particles, then you dissolve them in the same amount of volume in two different separate containers, you'll find that the salt that is finer dissolves faster in water. Why? Because their state of division or exposed surface area wasn't the same. So for the granule, a larger piece of salt, there was a smaller surface area. What do we mean? A smaller exposed surface area. What do we mean by that? Only fewer particles on the outside of the granule were exposed, whilst the ones that were inside the granule were hidden from reaction reaction with water. Then, but for the one that's ground finer, it means almost most of the particles were exposed to the reaction, which is dissolution. Now, if you go to the next factor, that is pressure, that is in gases. Pressure affects the reaction rate in gases. Why is it that way? It is because when you change pressure, when you're changing pressure, you're forcing particles together. When you're forcing particles together, they become crowded. As you would know from our previous video that was addressing the energies and the reactions that are involved in whenever a chemical reaction takes place, you'd remember that if the particles are closer together, the probability for them to collide is very, very high, and it takes lesser time for two particles to come together and collide, and hence the reaction rate will be higher when the pressure is higher, because the higher pressure is forcing particles closer together, making it much quicker for any two particles to collide and then react than it is when there is low pressure. If there's low pressure, it allows particles to be much more far apart, which will take then a longer time for one particle to approach the other particle that the chemical reaction can take place. And hence, the pressure affects the reaction rate just in gases, not in the other phase of matter, which is liquid and solid. Then the other factor is the nature of the reagents or the reacting substances. Now, naturally, some other substances will react much more slower than other substances. An example of that, if you think of the steel wool, which is iron, put in water. So when steel wool is put in water, it will take maybe a day or two for it to react with oxygen and then rust. But if you take the very same match that you've got then, and then you light it up on the surface of your matchbox, it will light immediately. The reaction, in other words, will take place immediately thereafter. Whilst you're just rubbing it off against the surface of the matchbox, that reaction then will take place faster. In other words, the reaction rate also depends on the nature of a substance. So explained further, one will say the temperature affects reaction rates. How does it affect the reaction rates? If the temperature is higher, there's going to be a higher reaction rate in all the phases of matter. And also if the temperature is lower, then the reaction rate will be lower. So again, with the concentration, the higher the concentration, the higher the reaction rate. And the lower the concentration, the lower the reaction rate. State of division. The higher the state of division, or the larger the exposed surface area, the higher the reaction rate. And also the lower the state of division, or the smaller the exposed surface area, the lower the reaction rate. In gases, the higher the pressure, the higher the reaction rate, and also the lower the pressure, the lower the reaction rate. So as explained in the nature of a substance, some substances naturally will react slower because of their nature, and some will react much more faster. So I think you are now ready. Before maybe we just go any further, I'll just explain a little bit of what I was saying and why did I say what I was saying. So with temperature involves energy. If you may just get reminded of what we said in our previous lesson about energies involved in a chemical reaction. So when the temperature is very high, the particles also have got a lot of kinetic energy. So that means since particles have got a lot of kinetic energy, there's a high probability that particles will move and collide with any other particle when their state of energy is very high. And hence, temperature makes reactions occur at a higher rate if it's higher. But when it's low, particles are sluggish, so they are very reluctant to move about, and hence it will take longer for any two particles just to collide in that reaction. When we can explain that in concentration, with the issue of the concentration, if I may just use two equal volumes. Now when the concentration is very high, it means I've got my particles very, very close to one another. So if, for instance, particles are very close to each other, it then means it will take much a shorter time for any two particles to come together and collide. That a reaction may take place. So therefore, but if you think of the concentration where it is low, it means it will take a longer time for one particle to come and probably collide with any other particle in the reaction vessel, and hence the reaction rate will be slower. Like I said when we talked about the surface area. So when we talk about the surface area, when a substance is ground into a powder form or it's finer, and then you've got this larger particle. For the larger substance, the inner particles will remain safer, whilst the outer particles will then only go into the reaction before the inner particles go into the reaction. When you think about pressure, if I may make an example of a syringe, so if you push a plunger in a syringe for a given amount of a gas that is inside, then it means the particles in that volume of a syringe will be closer together than is the case when the plunger of a syringe is not pushed in, that is, the pressure is very low. So on this side, we've got low pressure, and on this side, we've got high pressure. So I think naturally this is exactly what determines the rate of the reaction and why reaction rates occur the way they do whenever any of these five factors are involved. So maybe from now we'll have to look at our questions and then work on those questions. questions. Thereafter, I will come and make clarifications on why we answer the questions the way we will do. Thank you. You may pause the video.